Hello everyone, welcome back to my lesson. Today's lesson is about application of radar. You already studied about the radar theory, the SAR theory, and some information about the backscattering. So you already have many knowledge about radar. So the last thing I want to explain to you something related to the application, because you understand many things but you don't know how to apply to the reality. So this lesson focus on some application. So here I list some application and then show some example. The main application is firstly I have to say that the determine humidity and flood zone using the radar images. The other is we can draw the snow and ice boundary and measure the snow depth. The other is determine the soil parameters like geological structure and meteorite and mineral formation. The other, we can use the radar to find objective in the ground, under the ground, or can measure the altitude, like create this elevation model. The other, we can determine the land cover change and land deformation, like land subsidence, landslide, effect of earthquake, volcano eruption, or etc. The first example here, I want to show you that determine the flat area using Sentinel-1 images. Recently, maybe you be listened about the Google Earth engine, right? So it's very famous, the cloud space for computing the big data. So here is an example. I use Sentinel-1 images for detect the flat area in the middle of Vietnam. So you see in here in the Hue city around here, and in 2020 they have big flood in this area. So to detect the flat area, I just very simple take the before and after the image and make the subtraction between two images, and we can detect the flat area. Of course, we have to process something more like to mask out the shadow or mask out the water like lake or river, so we can detect the flat area like this one. And the other example, we can also detect the flat, but with this one more complicated because the flat under the forest. If with the optical images or the short wavelength of radar, the signal goes to the forest, it cannot go through the canopy to go to down to the surface. But in this case, with GS1 and ALOT Pansa, the signal can go through the canopy and hit to the waters under the canopy. So you see in here, for example, in this case, in this area, you see in this, at my point, at my mouse, in here, you see here is the river. The river has the black color, you can easy to recognize, but in this area is the forest. So the forest, you cannot see under the forest if the radar wavelength is short. But in this case, the radar's wavelength is 23 centimeters, so it can penetrate the forest very easy. So you see in here the flat under the forest with the white color. So you see in here, this is flat area. Yeah. So here it's open waters. You see this different color. So this is good, right? So easy to recognize. Here is 2006 November. Here 2007 January. Now in this area, there's nothing. You cannot see the water under the ground, under the forest, because now it have no water. But then you see, it changed a little bit. 2007 April. Here 2007 June. June now is rainy season. You see, it start have the water in here, right? So next is more. Yeah, it's more. And then when this water much and smoother, it create the black color like this one, right? Then, yeah, it's now September. Now November, it still exists, and then it changes, right? So December, now no waters, now dry season. So it still have moisture, but it's not so much. Now, January again, 2008. So there's no waters under the forest. So with this type of the wavelength, it's very good to detect something under the vegetation, because it can penetrate the canopy and even penetrate through the branch and go through to the ground. Here is application snow variation. When we want to detect the snow variation, we use the interferogram that I already showed you how to create the interferogram from one pair of images. So for example, in this case, they use the first images in December for 2017, and the second image is April, March 2018. That means different. So you see, with the first images, is when it creates the interferogram. You see the interferogram of these images, the fringes like this one is round, and then in here you see this is intensity images. You see these images. So also they combine, in this example, they combine with the Landsat image, the Landsat 8 images. So in here is the Landsat 8 images. You see in the band, in this band, you see the signatures of the snow. But in this time, from 2018, you see, before the snow is like this one, but after that it changes shape, and then when they create the face, it look like this one. And then you see with the Landsat 8 band 8, that means it's panchromatic, so it starting change, and the change is here around this one. So you see the fringes, it's easy to recognize. It's different before the fringe like this one, and after the fringe change to this kind of shape. So from this example, you can understand about how they use the pair of images to detect the change of snow variation. Here more the example of application for detect the geomorphology using Alert Panza and Landsat OLI in one areas. You see in here is the Alert Panza. Here is Landsat 8 images. So with the Landsat 8 and Alert Panza, they use the fusion method. Using fusion method, they combine two images to each other. So with this, the Alert Panza is very easy to recognize the texture of the object on the earth, but there's no color. But it takes the color from Landsat 8 in here to combine with these radar images. So the sea, here is the sea images, here is the combination between the radar and Landsat. The Landsat and radar images create images like this one. So the last one, this is zoom in into these areas. So you can see in here and in here, here and in here. So the dark tone arise due to the dark tone in this area. That means the sand. So sandy sediment is usually have dark tone because with sandy area it will have high reflection and low backscatter. So that's why the sandy area usually have the black colors. So with bedrock, the bedrock is will have high backscatter than the sandy area. So that's why it have bright color like this one. So this is for one example, very useful example. If you have the radar images, you can use the radars and optical images to combine to each other to have the application for geomorphologies. One very useful application is detect something under the ground. That means beneath the ground there's something. Maybe the wavelength can penetrate to the layer some meters to the earth, to the soil. For example, in this case, they use just one radar to detect all river of West Sahara Desert. The Sahara is now is a desert. There's only sand. There's no water. But when they use the L-band, just one, to take the photo, to take the images, acquire the images in this area, they discover some. You see, here is the river, the ancient rivers, like this one. The ancient rivers is beneath the sand. It's very surprising, right? So you can see in here is in Algeria. So this is a French team. They discovered and they believe that the river carried waters from water to the sea during the periodic humidity in the region, in this region, over the past 245,000 years ago. So water may last have coursed through the channel 5,000 years ago. So this is very good example of penetration under the layer of soil or sand. So in this example is sand in Sahara because it's very dry areas. It's very good example for detect something beneath the descent. Another example is DM generation. With DM generation, I already talked with you using two images. That means create interferogram. So in here, an example, here is optical images in this area. You see in here, there's vegetation. Here is maybe bare land or rock or something like this. So this is one example of this, but it is radar images. With the radar images, we have two radar images create the interferogram like this one. So see the fringes, that means the fringes show the elevation change that you already study in SAR lesson. So from this one, when we remove the flat earth phase, it shows like this one. And in here it is coherence, the quality of the pair of images. You see in here the coherence, that's rather good with the bright color is here very close to 1. Just only in this area is close to 0. That means low coherence in this, and this. And then after we have coherent, the correlation between the two images and interferogram, we can create the phase unwrapping. It's phase unwrapping, that means it's nearly like a dam generation. Is after that we can change from phase unwrapping to the elevation from here. So in this one we show it in the last this elevation model in grayscale in this figure. So this is an example of DM generation. Is very useful for you when you have the pair of images. High quality images can create the good DM. The other example is to detect the land cover change, land cover variation. In this case, I check with the change between two images from the first and the second. Just very simple to take the subtraction between the second and the first images. The second minus the first images to detect the change. After take the subtraction, you see something different. Different is going to create the pink color and blue color. That means the change in negative or positive, and we have to check what thing is positive and what thing is negative. That is the idea of change detection using the subtraction between the before and after something changed. Here an example of also land cover change using Sentinel-1 images. So here is one images in Bình Dương province of Vietnam, but in this area we combine to make the combination between 3 types of images. The first is 2015, the second is 2016, and the last one is 2017 of Sentinel-1 images. So you see in here something happened, like a blue color, like a magenta color or yellow color. But here in this area, white color, that means no change. The other is change. So we have to detect what thing changed like a blue and what thing changed it like a magenta, and the other is yellow color. So for example, in case we assign the first is red, the second is blue, and the last is green. Something is red, that means in this area is high backscatter, but after there's no backscatter. That means before maybe it had the maybe it's have barren, and then barren with the high backscatter. But then maybe they plant something, and they plant something. This is make the change like a magenta color or red color in this area. So when you have the exercise, I will show you how to detect the change and using Google Earth Engine to detect the change with the exercise. So now I have to move to the next slide. So in here, another example of application to detect the land subsidence. In this example, they use alert pulsar images, multi-temporal alert pulsar images to determine the subsidence using method PSINSAR in Jakarta, Indonesia. So PSINSAR, as I also showed before, is multi-temporal SAR images method. They use time series. There are many images, and it makes the one images master and the other is slave images create the PSINSAR and to detect the change. You see in here with the red spot in here is this some area with the minus value. That means the subsidence value in this area has subsidence, and the other in here there's no subsidence because it's nearly zero. And it has something like blue color, that means it uplift, but in this case there's no uplift. And the other information in another example is landslide detection. Here an example of landslide using the time series of 27 Sentinel-1 satellite images period in 2019 to 2021 in Yên Bái province of Vietnam. You see in here we also using the PSINSAR method and 27 Sentinel-1. In here with the red one is the landslide point. Here is the landslide. It around less than 20 millimeter per year in around this area and this area. And the other with blue color, that means no landslide. Here an example of identify the terrain change caused by volcanic eruption. You can see in here the annual interferogram showing land surface deformation of Okmok volcano in Alaska from 1997 to 2008 using EIS 1 and 2. You see in here the pair of images they create from 1997 to 1998 September, and the other is 1998 to 1999 from March from October to October 1998 to September 1999. So you see the fringe change from this one to this one also, and the last one from here the 2007 2008, the fringe absolutely change is different with this one comparing. So this is the method for detecting the volcanic eruption in the long gap from 1997 to 2008. So the last thing we can determine the effect of earthquake also. So here an example of Kumamoto earthquake in 2016 is very big earthquake, and it created the many fringe like this one. So here the centers, in the center is lost coherent. That means you cannot see the fringes, but outside it affect much and it create the fringe like this one. So the fringe show the change of the land, and it's easy to recognize the change in this case. And I also prepare the data for Kumamoto earthquake, and you can use the data that you can detect the change like this one. So I hope you can do the same and have the result like this one in the lesson. Yeah, that's all for today. Here is the reference. You can check the reference in here and check the Canadian website CCIS for more information about this. And thank you very much for your attention. See you next time.